Hi everyone, today we're going to be doing round 663. I decided to do this round instead of the Coder Grand Contest that also happened today because I want to do a contest where I can solve at least one problem. So that's my rationale for doing this, and I hope it's going to be enjoyable. Ideally better than last round was. So yeah, we're just going to get into it and wait for it to start. Let's see, so we can check and make sure nothing's changed, but I might as well. Yeah, okay. So I'm also going to be doing live commentary for this one. Just again explain my thought process. We'll see how that goes. Open up the trusty MS Paint. Hopefully I won't need to rotate any squares this time. But who knows? So it begins. Alright. Again, I'm going to open all the problems. There are only 5 this time, which is interesting. Okay. Subarrays. Nice. So that's fun. Permutation of length n. Okay. Permutation good if what? For every pair I and j. Given a positive integer n, I'll put any good permutation of length n. Okay, so we'll do test cases, c into n. Okay, so what we want is we want every bit to appear. I guess like we want the most significant bit to appear every 2 times. Then, yeah. So we could do something like. Well, I think just any permutation works because the I'll like the bitwise OR of any 2 numbers is at least as big as the maximum number, right? So I guess I'll just explain this later. Yeah, I'll explain this when I get a better grip on the problem, or it fails. That might happen too. Maybe it will fail. Okay, so you just print any permutation. That's a cool A. I guess anyone who accidentally submits anything will solve it. That's funny. Alright, so yeah, I'll explain that one after. It's a conveyor belt, so label ij. Everything has a direction. variable is called functional if and only if any luggage reaches the counter. Any luggage placed in the cell should eventually end up in the cell NM. Okay, so if you start anywhere really, you're going to, like, let's say you have something like this. This way, this way, this way, this way, and this way, and then we'll just draw some of these. No matter what, you're going to end up on the back row somehow, on either this column or this row. So all you need to do really is make these functional. So you just see how many of these aren't right and how many of these aren't down, and that should be the answer. I think that is correct. So scene to end M, string mat, I'll just use the power of my macros. So for I and if mat M minus 1, I is not equal to C, and mat, oh actually I can do for I M minus 1. Then we want all of these to point down. We'll set answer equals 0. Then for I M minus 1, if, oh wait, this should be, this is the row, that's the column. Mat, that A is still funny. The biggest chore where you can print literally any answer. R plus ants. Yeah, ants. Okay, these are conceptually nice problems. I'm liking them. Should be 1390. Okay, and that's just true. So yeah, essentially all we care about is the last column and the last row, because no matter what, we're going to end up in at least one of those. Let's check it again. Oh no, not Q issues again. Okay, good. Okay, we have A and B. See how the solve rates go. Alright. I guess we're not zooming through, but we're fine. Just read the input right now. We have a single integer n. Okay, we give it another permutation. Build a graph of size n. For every I, find the largest j such that... Okay, let's illustrate the example. Both for myself and for you guys, I guess. Sorry for that spacing. We'll switch here, and for every I, find the largest j such that j is less than I and that is greater than that. So for example, this would cause an edge here, and it's undirected, so that would cause an edge there. And for every I, find the smallest j such that j is greater than I and it's also greater. So that's here and that's here. Okay. And what else? 4 doesn't, wait, what? Oh, 1, 3, 2, okay, right. That also has this edge. Okay. So we have 1, 3, 2, 1, 2, 3, 4, 3. So that's what this looks like. And this does have a cycle. This better not be asking for n factorial. Okay, good. Enough of these troll problems. So we ask if there's a cycle from this graph. Alright, so we read in n, we do some math, we print an answer, and we have fun. So what kinds of permutations actually, wait, hang on. 4 factorial. 24. So there are 8 permutations that don't create cycles. There are 16 cyclic permutations for n equals 4. 4, 2, 1, 3 is one such permutation. Having a cycle of, so 3 would go to 4, wait, 2 would go to 3, 3 would go to 4, what? So 3 and 4 have an edge, 2 and 3 have an edge, 1 and 3 have an edge, 1 and 2 have an edge. Okay. So what kind of permutation doesn't form a cycle? Wait, actually, this is another cycle, right? So 2 and 3, 1 and 3, 1 and 2. Yes. So any kind of straight line, right? So let's make the graph for 1, 2, and 3. So this will have an edge here, and this will have an edge here, but there won't be a cycle. Let's say we had this over here. Then we would have an edge here and an edge here. So my guess is it would be nice if they listed out all the permutations that aren't cyclic, but that would be giving away too much, I assume. So about 1, 3, 2. That forms an edge here, that forms an edge here. Okay. So any cycle will be of the form, let's say A, B, C, where, for example, here. So B is less than C, and B is less than C, which is less than A. Is that the only form of cycle, or are there more? How's this one going? I assume it has fewer solves because it seems harder. Okay. So is this the only form of cycle? What if we have something like 3, 1, 2? This, wait, no, it's the same thing. Yeah. So we'll say we put 3 here. I'm assuming every cycle is of length at most 3, because everything is attached to the thing that's, or if there's a cycle, then there's one of length at most 3. That's an assumption that I don't have a proof for, but it seems kind of intuitive because everything would be small. So, like 3, 2, 1 won't have a cycle. 3, 1, 2 does. Let's see, 2, 3, 1 doesn't, because that element is in the middle. 2, 1, 3 is a repeat of this. Then 1, 2, 3 is a repeat of that. 1, 3, 2 is a repeat of this. So, yeah. So there's one kind of formation that does make a cycle. And it's this. So how do we exploit that so we can count things? I think we can't have any local minimums. That is, the permutation has to be bitonic, as in, let's say we have A, B, C, D. Then there's some split point, let's say B, such that A is less than B, which is greater than C, which is greater than D. So at some point it has to be increasing and then decreasing. Because otherwise we're going to have a situation where we have A is less than, if A is greater than B, which is less than C, and then we'll get this case. Yeah, and it doesn't matter the values of A and C because no matter what, like one of these will be greater than the other, and then we'll have this type of situation. So I want to count the number of bitonic permutations. And what does that entail? Okay, so obviously B has to be N. So we have, zoom out, no, okay. I'm gonna clear everything because this is kind of getting a lot. So we have N, drawing please. So we have N, then something, and something. And let's see. So there are N possible positions for N. 1, 2, these are the positions that N can be in. Sorry, this is terrible drawing, but wow, this is remarkably terrible. But I mean, we just fix the position of N, then we need to figure out how many elements go into each dot dot dot. It doesn't matter what elements we put in, it's just the elements that we have. So it's essentially N minus 1 elements we have. Then we choose, I think just I. Yeah, so it's N minus 1 choose I, and it's the sum of that. So let's do some factorials. This is how you do combinatorics. You create an array called factorial of size 1,000,000, and then you can do inverse factorial as well. And then you have some sort of modular inverse, which I have as a template. Feel free to copy this template. You can find it in my submissions, or just, I guess, create your own. So fact 0 equals fact 1. There's technically a way to compute inverse factorials in OVN, but it doesn't really matter. Set these to 1, then 2n. Fact I equals I times fact I minus 1, mod, then I fact I, modular inverse of factorial of I. Then we write a method function called n choose k. Denominator equals the inverse factorial of n minus k times the inverse factorial of k. This is a standard formula. Then return fact n times dem mod. Okay, now ans equals fact n. For in, ans equals m sub. That's basically subtracting nck and I. That's basically it. It's all possible permutations subtracted by the number of ways that we can't. Okay, that's great. Oh wait, yeah, okay. There's something wrong with that. Why is there something wrong with that? Oh, and actually, there's a better way to do this. It's because it's the sum. Oh wait. So the sum of all. Huh. Interesting. Yeah. So the sum of all n choose k is just 2 to the n. If we have, like, the sum of all n choose I is 2 to the n. So we can essentially subtract 2 to the n minus 1. I think that will work. For what? Oh wait. Because fact n doesn't exist. For 16. Let's check this. Okay, that's the answer. So it's just n factorial minus 2 to the n minus 1. That's the final answer. Interesting, I guess. That took a while because I'm not that fast at combinatorics, but I guess we're fine. Let's check the standings. I mean, imagine in terms of speed we're not great, but yeah, we can catch up still. Okay, binary matrix is called good if every even length square submatrix is an odd number of ones. Another, the terms above have their usual meanings. Nice. Binary matrix is one where every element is 1 to 0. Submatrix is rectangle. Submatrix contains all elements. Yeah, even length square if it's a square and its side is even length. Cool. So every even length square submatrix has an odd number of ones. A 1 1 to 0 and A 2 2 to 1. How does that work? Okay. So basically writing the whole factorial thing was, yeah, that's just clarifying the statement. So basically writing the whole factorial thing is pointless, but I mean, I guess it works. C into n to m string ss. Guess we're gonna make this local. Alright, actually, because n is less than or equal to m, then n is at most 1000. So we can do that. How's this going? I assume there's some sort of pattern that we can use where why do they have the constraint that n is less than or equal to m? That's interesting. Okay, so this is okay. I see how this works. Because let's say, oh my god, these problems are hammering it in with the observations. Okay, so let's say you have 4 square submatrices of size 2, right? So these are all 2 times 2. Then this big thing is 4 times 4. But all of these are odd, right? So we have odd, 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 odd. So we have odd plus odd plus odd plus odd. And 2 odds summing together is even. So we have even plus even. Then we have 2 even summing together is even, so we have even. So in any case, if we have any group of 2, if we have any 2 by 2 group of 2 by 2 submatrices, then it's not possible. Because these have to be odd, but at the same time, the whole thing has to be odd, and that's not possible. So what we can do instead is, essentially, m is the greater one. So if m is greater than or equal to 4, there's no answer. Because if it is, then we end up having the scenario above. No, wait, if n is greater than or equal to 4, then we always get the scenario above. So now n is at most 3, and I see these constraints make sense now. So if n is 1, then there are no even length square submatrices. So we don't have to change anything. Otherwise, what we can do is we can kind of I'm thinking of what are the constraints? 1 second. Okay, I'm thinking of a kind of a bitmask DP where we It's kind of annoying in that way. I think that should work, where we do kind of a bitmask DP on, so LO DP. We can do int DP 100,005 and 3. No, 8. And essentially this represents where we're on the ith column, and the previous column has this mask of bits set. Yeah. So what we can do then is we can compute the mask of each column. And we do that by saying for im LL b equals 1 for jn. Then we keep track of the current mask value. Then we say mask val plus equals MSB times SS. And this doesn't really matter. We might as well make this huge just to be safe. SSI. No, SS. The jth row and the ith column. And then subtracting the character 0 will basically mean it's 1 if it's 1 and it's 0 if it's 0. So that's perfect. Then MSB times equals 2. Then for I LO max equals 2 to the n, which is at most 8. And I'm just going to make this 9 to be safe, even though it doesn't matter. For I 8, no, max dp 0, I equals. So what we can do is we can create a difference function, which is essentially asking how many bits do we need to change to make A to B. And that is the number of bits set in A XOR B, which you can count with the function built-in pop count, which is the cool STL thing. And then we do it for A XOR B. I'll leave it as an exercise to find out why that works. Diff. So mask, oh wait, I should do mask I equals mask val, mask I, and I. No wait, mask 0, sorry. And then for I1n, we only want to set the masks where it actually works. So for j max int v equals. And we also look at the previous mask. So int d equals diff j mask I. This is the current difference we have, and then we have to check if it actually satisfies the condition. So the way we do that is bool possible is 1 for I m minus 1. We're just going to check both squares. Int count equals I'm gonna do some bitwise magic here. So this basically checks. This basically counts the number of bits in the first two. Counts the number of 1 bits in the first 2 bits of. Yeah. Sorry, I'm gonna illustrate why all this bitwise magic works once I explain the solutions. But for now, I'm just gonna write it. Essentially, this checks the number of ones in. If it's 3, it's the first 2 bits, and if it's 6, it's the second. It's the second and the third bit. Okay. Plus built-in pop count j. If count mod 2 equals 1. If it's even, pause equals false, break. So then if pause dpij equals for in for jm for im for jn dpij equals, let's say, infinity, only 8. I'm gonna use this more efficiently. And equals inf. So if pause dpij equals min dpij diff plus dp I minus 1 prev mask. That's essentially our condition, our transition. Then for I8 min ants dp and m minus 1 I. If ants equals inf cout -1. Okay, let's check the indexing and just make sure this works, because usually we do dp by n and m, so it's kind of confusing. So for im, yeah, ssji, so we're just doing that. Mask I, okay. Now let's just print this, just to be safe. Max equals 2 at the n for in. For j max, that's scary. Should not have done that. For I max, okay, so this should be up to m. For j max, for prev mask, this should be n. Then this will be val equals 3 times I plus 1. This is essentially part of the bitwise magic that we're doing. Yeah. Alright, let's check it. Okay. I'm assuming it's because it's int. Yep. Cool. And we actually get 2. Wow. 5, 4, 3. Obviously, it should be -1. Wait, what did I just... Okay. So A, 1, 7, 0. Obviously, it should be 0. Let's check it for 2. 0, 0, 0, 0, 0, 0, 0, 0, 0. What? How does that work? Shoot. Let's see. Oh, wait. Max, right. So we don't have any other magic constants, right? Except for n is greater than or equal to 4, or n is equal to 1. We always use max. Yeah. Okay. Cool. 2. I guess we set this one and then this one. Perfect. Okay, let's try it. I think it should work, hopefully. Pretest 9. Pretest 16. Let's go. It's a lot of pretests. Sweet. How are we doing? 33rd. Nice. All right. Okay. Lecture master. God. Okay, so again, I'll explain the bitwise magic after. It may be kind of cryptic for now, but it's kind of intuitive to understand once you understand like how bitwise AND works. So yeah, I'll just explain it after this. How many people solved E? One person, and it is an orange who's doing the problems backwards. Interesting. Check how I'm doing. Down to 35th, I guess, because I had a slow C. Yeah, but we have no penalties so far. Looks good. It's much better. Okay, you have a simple and connected undirected graph consisting of n nodes and m edges. That's a scary long input section. Sounded like it was interactive for a second. Okay. Alright, just gonna these some big constraints. Consider any way to pair some subset of these n nodes such that no node is present in more than one pair. This pairing is valid. Oh my god, it's one of the following things. So you have to solve exactly one problem. So this pairing is valid if for every pair of pairs the induced subgraph, okay, containing all 4 nodes, 2 from each pair. Now for every pair of pairs. What does that mean? Okay. So for more people solving this? Okay, who else has solved it? Let me guess. Let me have a guess. Is it Rainbow? He has solved it. Pretty much. Because he always has problem sets backwards. It's kind of funny to watch. Okay. It's also a crazy amount of pretest. Jeez. In fact, we can see, no, never mind. It's not really that important. For any 2 pairs, A, B, and C, D, the induced subgraph should have at most 2 edges. Yeah, so it's essentially just the graph with only those 4 vertices for each pair of pairs. Okay. Please note that the subgraph induced by a set of nodes contains nodes only from this set and edges which have both of its endpoints in this set. Now do one of the following. Find a simple path consisting of at least CL n over 2 nodes. So let's define the requirement. So we're going to have to do some DFS graph algorithms, so we're going to make that global equals m plus 1 over 2. That's CL n over 2. Or find a valid pairing in which at least CL n over 2 nodes are paired. It can be shown that it's possible to find at least one of the 2 in every graph satisfying constraints. So generally you can show that if one is not possible, then the other must be. Generally that's the case. Okay, let's just read the rest. Each test, hopefully, oh my god. Okay, so there are multi-tests, which is even worse. VI edges 500,005, not 5,000,005. So 4 IN edges I dot clear. Use some dangerous macros. Okay. Before we do that, I'm just going to check one more time. Who else has solved this? Lin. Okay. So my place is relatively secured. I hope. Only because I was weak on C Yeah. But that's fine, because we have a relatively intuitive explanation. Comes down to kind of speed forces, but not really. I guess once people start solving E, it's going to matter more. Also, there was no interactive problem. They lied in the statement. Although they didn't really lie. They just said you should be prepared for one, I guess, to scare us, and then they don't have it. It's kind of sad. Okay, so awesome. So the path output in the first case is the following. It's just the exact same thing. 6, 5. Yeah, they just give us the same graph, or it's possible to do both. Okay. So one is a pairing invalid. Let's see, this pairing would also be valid because that would only have one edge. This pairing would also be valid, and this pairing would not, but this pairing would. Doesn't really make sense because I'm just waving my mouse around, but there's some logic going on here. Okay. So what does a simple path have to do with such a pairing? And how do we find the simple path? That's also a thing. Because this has a simple path of length 6. And that is the maximum length that a simple path can have here. I think. Right, like if we 2, 3, 1, 2, 3, 4, 5, 6, yeah. Okay. So there are two types of pairs that we can make. Pairs where there are an edge between the two paired nodes and pairs where there aren't. And if we use, let's say we have two pairs with an edge between both of the paired nodes, then we can't have any edges. Like let's say we paired 4, 10 and 2, 6 in this graph. Then that wouldn't be valid because we have an edge here, an edge here, an edge here. It's kind of a hard graph to do. But if we paired 1, 4, and 3, 6, that would be fine because even though both of these have edges between them, there's no edge between like the pairs. There's no edge between vertices in different pairs, so that's fine. I don't see how that's helpful. Assuming this is important. Also assume more people are solving this. Okay. Find a valid pairing in which at least n over 2 nodes are paired. Wait, this is messed up, isn't it? The Soren distribution is different. Yeah. It's 2750. How many points do we have? Okay, so we have 41xx. Nice. How are other people doing? Go Java. Man, that guy needs to get to CM. Okay. Wait up. This is weird. Did they? Okay, I guess they fixed that now. I don't know why that happened before, where it was slightly messed up. That's kind of a roast. Okay. It's funny. And that's loud. I already solved that, so not a big deal. Still have A, B, and C, D totally clean. So that's a good thing, at least. I have kind of a monotonic submission time. Alright, so here's the part where you get to watch me stare at a screen. Or you get to stare at a screen. While I'm staring at a screen, just thinking about this. So I guess we can draw out some stuff, like... So we have such a graph like this. Okay, this is small, so... Like the general idea is, if there's a simple path, then there's a lot of edges. And if there's a valid pairing, then there aren't that many edges. Because the more edges there are, the easier it is to make a simple path, but the harder it is to make a pairing. So if we can prove somehow that if there is no pairing, we can make a simple path, then we can do that. What if we just start at some vertex? Okay, they definitely don't want n squared here. Or even, what is it? M root n. Yeah, that might be too much. Especially because graphs are not friendly for constants, kind of. With the cache, at least. So, here, there's definitely a pairing. This is kind of what we're thinking of. So these samples are not great because both of them have, like they have both pairings and simple paths. Let's say this. So if we paired these, okay. Oh, that's kind of interesting. So if we have any invalid pair, yeah, wait. So if we have any invalid pair, that means there are at least 3 edges between them. Which means that there is a path that goes from one of these n vertices to the other one of these n vertices. So if for any failed pair of pairs, there is a path that goes through them. Which is cool. But why is it cool? Maybe let's just do a sort of greedy approach where we just like does greedy work here? Let's say we initially try some pairing. and so we try a random pair, I guess. Or an arbitrary pair. We start off with an arbitrary pair. Then either the pair works or it doesn't. So if it doesn't, then if the pair works, then we found a pair. Otherwise we have the start of a path, I guess. Oh, that's not too helpful, because what if we have a pair like this, where like if we have a pair like this, then this creates a path, but this path isn't very helpful. Because we can't do anything with this path. We can't extend any further. That's kind of a hard case. But we do at least have a path of length 3 that we get from it. So we use 3/4 of the vertices from this path. Right, now let's say we take another arbitrary 2 vertices. So let's pick a vertex where we extend this path from. Then we pick another arbitrary 2 vertices, or 2 pairs, let's say these 2 and these 2. I'm gonna copy this in, I guess, so I don't have to wave my mouse around. So let's say we initially pick these 2 pairs. So these 2 pairs are invalid because we have these 3 edges. But we can create kind of a path like this, where it's of length. What defines a simple path? Nodes, okay. So we get initially 3. Then let's say we pick another arbitrary pairing. Say these. Now these pairings are valid. So now we have a pairing. But then what? So now these just happen to form a valid pairing. But if they didn't, what would we do? Let's say we had edges here, here, and here. Or, to make it harder, here, here, and here. Then we would okay, so we can extend the path by 3 here. So maybe that's all we have to do. So let's say we start with an arbitrary pair, then all we have to do is we make it so Well, we can't just pick arbitrary pairs. Can we? Because a hard test case I'm thinking of is something like just a graph like this, repeated a lot of times. Maybe just a bunch of complete graphs like this, and then we'll just take a lot of these. Right now, the issue with this is that we have many valid pairings, but they aren't connected to each other. As in, like, this would be a valid pair, for example, because these have no edges together at all. Does it say the graph is connected? Oh, connected. Okay. So maybe this isn't possible. Let's say we did something like this, right, where we connect these kind of arbitrarily. And we'll just connect them like this. Then what do we do? Well, then this works, I guess. Okay, connected is interesting, actually. Does that make it more possible? As in, does it matter if it's connected? What if we tried something weird like a DFS trick? Yes. Why would that help? Don't think it would. So do we only have to print the nodes? That would be awesome. Okay, good. We don't have to print the edges, which is nice because if we pick two pairs, then that's fine. So let's again go back to this test case. Say we start with an arbitrary pair. Then we decide that, say we start with an arbitrary pair. Let's say these, right? So we find a pairing here. So this is a valid pair, so we just take it and we continue looking for an arbitrary pair. Then we find one that is invalid. Now we want to extend that somehow. I think what we want is as few vertices as possible from the pair to be kind of on the frontier. That is, the set of nodes attached to the pair. We want exactly one of them to be on it, if possible. That way we can extend the path as far as we want. Note that if they're now even like square sub matrices, so n equals 1. So what will be bad is if we get some path. Let's say we get some long path. To almost n over 2. So what we need is to be able to, if we have a pair that's invalid, that is, has more than 2 edges between it, we need to use all of the vertices on the path. Otherwise, it may not be possible to do some sort of greedy. So we start with 2 vertices that are connected to each other, like these. This sample is a friendly one, but there are some very not friendly ones. Actually, are there? Maybe n equals 13. Because then we need a path of like 7 or 7 nodes to be paired. Let's see, how are other people solving this? 16, okay. It's not bad so far. 42nd, okay, I can take that. Although I see more people are going to solve this by the end of it, so I mean, we should keep trying, obviously. Also not bad. Are there any hacks or anything? Doesn't look like it. If I go to the hacks tab, it's only going to show my own, so that won't work. Who has solved this? Okay. And they're all kind of not light on the time limit except for this one. I might just be able to like get rid of this. It's very painful to look at. Oh my God. Okay. So let's snip this again. Might just be able to do some sort of like DFS. Like we go here, then we go here, and we pull all these nodes onto like a stack or something. Then once we have 4 nodes in the stack, we see if there's a pairing between them. If not, then we can, so if there's a valid pairing, we just add it to a list of pairs, otherwise we extend the path by it. So a possible issue with that though is maybe we get some sort of disconnect pairing like this. Where this node is very screwed. And actually this totally cuts us off. I think I'm thinking about this wrong. Yeah, because I'm thinking about just adding pairs in individually, but it has to work for all pairs of pairs also. Not just, like we're not just adding subsets of 4 nodes in. So maybe we're, so we start with some arbitrary pair again. Then we try 2 nodes. And we ask, does it work with the pairs we have? And if it does, then we add it. And if it doesn't, then we try and extend the path that we have. Say we start here arbitrarily, then we'll go here and then visit this. Then this pairing doesn't work, so we I guess we can start a path from it, right? Then I think if possible, we want all pairs to be between adjacent nodes. Maybe that's not even possible though, because like we have this and here. And this is an invalid pairing with this. But we only get 1 vertex out of it. That's the issue. that if we're going to kind of sacrifice a pair to be used as the path, we want to be able to get both vertices out of it. Some dramatic word. Because we could, let's say, add some like edge like this, and we could say to 13. Right? Then what we'll do is I don't think there is a path in this test case. Because we can go here, here, 3, 4, 5, 6. No matter what, it's still at most like 6, I think. But CLN over 2 is 7. So we can make a valid pairing kind of like that, and like this, and like that, and that will work. Because in fact, none of these pairs have any edges together. How do we find that? Let's see who else has solved this now. Assuming more people are solving it. Yeah. Okay, so what if we... Let's try to find a graph where there just is no pairing. Obviously there's a complete graph. You can just say... So this works. This also has a cycle that spans the whole graph. So let's try and come up with a bigger case. 1, 2, 3, 4, 6, 7, 8, 9. Right? Okay. So we also want the path to be short. Let's say we just have a star graph. We have everything that's connected to one vertex. That does have pairings though. For that we can just group these together, and these together, and these together, and these together. And they all work, and none of them have any edges together, as long as we don't include the star. So we overkill it here with the pairing. So star graph is like the opposite of where we want to go. So we have this, and that. Here we have both. Yeah, we have both here. We can make this a pairing, this is a pairing, and this is a pairing. So that works. Or we also have some path that in fact spans the whole graph. So what if we just have a tree? You can get some insight from solving a tree. 1, 2, 3, 4. So here, let's just say something like this. Now this still has a path, so we need to add 2 more vertices. Say that, and that. Okay, now this has no path, because every path is of length at most 5. So in this case, if we're taking a leaf, then we're just good. So either we have a lot of leaves or a large diameter. That's how that would work. because the diameter is less than n/2. There'd be a lot we can do. Okay, we'll just check my friends again, see how hard this actually is. Okay. What are the wrong answers here? Some of these people started with, I guess, bad approaches. It's 14. Being honest, I'm not really sure what to do here. What if we think about degrees? So we have a lot of vertices with high degrees. How quickly is the salt count increasing? Check again now. Okay. So in this case, we can make a pair of all, like, leaves. We also do stuff like this. Yeah, there are many things we can do. So the one thing we found to relate the two things to each other is that let's say we pair all nodes with each other somehow. Like let's say we use all three of these as pairs, then if a pairing is invalid, then it creates a path of length at least 3. What if we just created a totally random pairing? Like we just pair 1 with 2, 3 with 4, 5 with 6, for example. So we did it here, 1 with 2, 3 with 4, 5, 6, 7, 8, 9, 10, 11, 12. Then two pairings. Like if they don't cooperate, there has to be some connection between them. So for example, with this, 1, 2, 3, and 4 are valid. 1, 2, 5, and 6 are valid. Actually, all of these pairings are valid, so that just works. So we have 1, 2, 3, 4, 5, 6. Then these pairings would be invalid, which means we get a path of length 3 out of these. I think it still doesn't work somehow. I've had multiple similar problems in the past where, if I recall, there was one, or was it 649, where this problem, where we either do something here, and we kind of relate these two. And this one, yeah. And then there was another one around 628, where it was kind of the same idea. And we find one of these two things. And this is either a path or that pairing they define. This one I didn't even really solve. I just kind of guessed something and it happened to be correct. Not really sure what I can do about these. Oh, second thread, got it. Okay. was him. Tree case is not very helpful. Not really sure what else to think about now. Okay. Okay, so I don't really have any leads on this one. My guess would be that the general idea to create the solution is again to, like, you have to somehow relate these two because these are both, individually, they're both, I think, hard problems to solve, but somehow there's some algorithm that either finds one or the other. Yeah, I'm not really sure what to do. What's the status on E? Let's say pretest passed, and I'm not sure if this is based on input, but all of these have some high run times, except for this one, and I guess this one, maybe. So either it's input or it's, it's kind of complicated. Might be a log factor in there since there's a 3-second time limit. Anyway, I'm not really sure how to do it. And I also don't think there's enough time to implement it. So I guess I'll just finish by going over the solutions that I did get for A to D. Just open those. Okay, so for A, we can solve it with basically the construction of, like, any permutation works essentially. 1, 2, 3, 4, 5. Actually, is there any permutation? It might not be any permutation, but specifically this one. No, I think it is any permutation because if a subarray has, let's say, 3 elements, then the important thing is A or B is greater than or equal to the maximum of A and B because, or the maximum of A and B because, well, you're still keeping you're keeping all of the bits that are in A and B. So doing an OR operation will not decrease any of the numbers. So because of this, no matter what subarray we have, any subarray that has 3 elements, for example, because all elements are distinct, it will also contain an element that's greater than or equal to 3. And a subarray with 7 elements will contain an element that's greater than or equal to 7. Again, because all elements are distinct. So the worst case is essentially all subarrays that start in 1, and either way, they'll have length x and they will contain the element x, which means that this will be true that the bitwise order of the elements in the subarray is at least as big as the number of elements. So essentially, the solution is any permutation. And it's kind of a chore problem where you can literally print any type of input and it will work. Okay. Here, any output. Okay, B we also kind of went over, but I'll do it again. The idea is no matter what you do, I'll make a bigger conveyor this time. No matter what you do, you're always going to end up on one of two things. I'll just draw some random stuff. No matter where you start, you're always going to end up either on, let's call this the final point. You're always going to end up either on the last column or the last row. Yeah, because you always have to go either down or right, and essentially if you're not here, then going in one of those directions will take you closer to one of these squares. So no matter where you start, you'll always end up somehow on the last column or the last row. And therefore, you're also allowed to start on the last column or the last row. So you have to be able to get from the last column or the last row to the final destination. So in fact, all of these, it doesn't matter what they are. The only thing that matters is that all of these go down, because if this goes right, you're just stuck. And all of these go to the right, because if it goes down, you're also stuck. So you just have to count how many of these aren't already pointing down, in this case this one, and how many of these aren't already pointing right. And that's your answer. So you just check for the last column and the last row, essentially. Yeah, so that's O of n plus m, although it's nm for the input, so you have to read that anyway. Let's go to C. For C, so again, if you have any type of, let's say for example, 3, 1, 2. So you're going to have an edge from 1 to 2, an edge from 1 to 3, and an edge from 2 to 3. So this does have a cycle. And more generally, if you have an elements A, B, and C, where essentially B is less than A and B is less than C. So B is less than min A, C. This also means B is kind of a local minimum. That is, it's between two elements that are greater than it. So if you have any local minimum, then you're going to have a cycle with these three elements, because you're going to have an edge from B to A, an edge from B to C, and because one of A or C is greater than the other, you're going to have an edge from A to C. So there will be a cycle here. So what that means is that you can't have any local minimums. So let's say the permutation is like A, B, C, D, E, F, G, H, and so on. Then fix that. Then essentially what you have to do is, this has to be kind of like greater than, let's say this is less than this, fine. So then we have this is greater than this. Now if let's say we have a chain of greater thans, right? If we ever have an element that's less than E, then E is going to be, or if we ever have an element that's greater than E to the right of E, then E is going to be a local minimum, and we'll have this situation. So essentially, as soon as we have an element that's greater than the adjacent element, all of the rest of the elements also have to be greater for there to not be a cycle. Yeah, so specifically we're going to count the number of permutations that aren't cycles. So yeah. And so there's a specific sort of criteria we have here, that a permutation that doesn't have cycles is going to have some elements that are less than something and some elements that are greater than something. So all elements are distinct, which means that here we're going to have the position of n. And doesn't really, kind of doesn't matter. Or no, it doesn't matter where n is, but it doesn't matter what elements we have on either side, because no matter what, they're going to all be distinct, so we can have, there's exactly one ordering of whatever elements we have on this side, and similarly on this side. So all that matters are the position of n and the elements themselves on either side of the permutation. So let's say we put n in the first position. Then there's only one way to put the rest of the elements on the right, because all the elements have to be on the right. Let's say we have this. Then we have 7 elements that can go on either side, and we have one position we put one element on the left and the rest of them on the right. And so here we put 2 elements on the left and the rest of them on the right. So essentially, wherever n is, let's call it I, where it's 0 indexed. Let's call it where permutation of I is equal to n, where I is in the range of 0 to n minus 1, so it's 0 indexed. We can put it in any of these positions. Each time we're choosing from the elements of 1 to n minus 1, we're choosing I of them to go on the left, and then the rest of them will go on the right. So we sum up, I'll make this a different color actually. We'll sum up from I equals 0 to n minus 1 of, we choose I elements from m minus 1 total elements. Right? So essentially this comes out to 2 to the m minus 1. Now there's also a different way to think about it. We can just say for each element from 0, 1, 2, 3, 4, 5, etc. we can kind of say either it's on the left or it's not. So for example, L, R, L, L, R, L, right? Now each element can be, actually wait, this should be just 1, 2, 3, 4, 5, not 0, then dot, 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 n minus 1. So each element can independently be on the left or the right. And each element has 2 possible states that it can be in, and there are m minus 1 elements. So essentially there are this is a different way to get 2 to the m minus 1 different possible states, or different possible permutations, where each is either on the left or the right of wherever n is. So 2 to the m minus 1 is the number of permutations that don't have cycles. And we're asked to count the number of permutations that do have cycles. So a well-known thing is that there are n factorial permutations in total, which is n times n minus 1 times n minus 2, dot, 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 all the way down to 1 times 2 times 1. Because think of it this way. We have let's say we have 5 positions and we're taking a permutation of length 5. We can put 1 wherever we want. We have 5 different places to put 1. Then once we place 1 down, we have 4 different places to place 2. Once we place 2 down, we have 3 places for 3, then 2 places for 4, and then there's only 1 place left for 5. And this formula basically holds for any length permutation. It will always be n times n minus 1 times n minus 2, etc., which is n factorial. So that's the total number of permutations we have. Then we subtract out the number of permutations that aren't cyclic, which is 2 to the n minus 1. To compute both of these, you can either do them naively or use some fast modular tricks. But essentially all you need to do is make sure you don't overflow by constantly make sure you don't overflow. All you have to do is constantly keep taking elements mod the 10 to the 9th plus 7. So something else that's interesting, permutations that are, or just arrays that are like this in general, where you have A is less than B is less than C, where it's strictly increasing and then strictly decreasing. These are called bitonic. It's just kind of a term. It doesn't really matter, but possibly if you had found out this observation, instead of just working out the math, you could search up like number of bitonic permutations. And maybe that will give you an answer or something. Yeah, so you can get 2 to the n minus 1 here. Why would it be minus 2? Okay. Okay, so they don't count like 1. They don't count like 1 to n in order. Although we should count that because these are also invalid. So essentially, yeah, it ends up to 2 to the n minus 1, and you can find that in many different ways. Now we go to D. D is cool. You're given a binary matrix, which is essentially a matrix of zeros and ones. So let's take the sample 1, 0, 1, 0, 0, 1, 1, 1, 0. And you want to make it so every even length square submatrix, which is essentially, you have to have a square, first of all. So it has to be, a submatrix is just like a subrectangle of elements from the matrix. So it has to be a square. So these are the possible ones, these 4 in this messy diagram. Then, actually I'll make these different colors. Should be easier maybe to follow. So all of these are square because they have the same number of rows and columns, and they also have to be even size. So like 2 by 2, 3 by 3. This one is not valid because it's not even. And this one is not valid because it's not square. So those are some examples. And we want every even length square submatrix to have an odd number of ones. Now there's something quick we can observe here, which I kind of went over before, but I'll do it again. So let's say we have this square, and then copy this, I guess. No, that's not going to work. Alright, let's just say we have this square, this square, this square, and this square. Cool. Now, it doesn't matter what these are. Let's just say these are of even length. Let's just say these are of even length, like 2. Then this whole thing is 2 times 2, which is 4. So each square is 2 by 2, and the whole thing is 4 by 4. Now, all of these 2 by 2s have to have an odd number of 1s inside them. So, for example, say this has 3, this has 1, this has 1, this has 3, this has 1. But what this means is that this 4 by 4 matrix is going to have an even number. Because if we add 4 odd numbers together, Well, if we add two odd numbers together, we get even. So each row has an even number. And then we add these two together, and then we get another even number. So no matter what we do, if we have any group of four 2x2 submatrices in a square like this, because both the 2x2s and the 4x4 has to be odd, it's actually not possible. Yeah, because of the fact that odds sum to an even number. So what this means is that if we have any 4x4 submatrix at all, there is no answer. Or it's not possible to have such a matrix. So what this means is, because n is less than m in the constraints, the number of rows is less than the number of columns, if n is greater than or equal to 4, there's no answer. So now we know that, I'm going to get rid of this. So now we know that n is less than or equal to 3. So we have at most 3 rows and as many columns as we want. Now, this is always possible to do, I think. Yeah, it is always possible to do. There's a construction like, for example, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, dot, dot, dot. All of these squares are going to have exactly 1, 1 in them, and it's going to work out perfectly. So there's, wait, no, not this. Sorry. It should be like this, 0, 1. Then 1, 0, 0, 0, 0, 0, 1, dot, 1, dot, dot, dot. Because all of these, yeah, this should be right. Because all these squares are going to have exactly 1, 1 in them, so it'll be odd and it'll be perfect. So it's always possible when n is less than or equal to 3. So if there's one row, then there's only one, like there are no even square submatrices, so automatically it's valid. So if n is 1, this isn't necessarily a special case you have to handle, but actually it is, kind of, the way it works. So n, add this to the list of special cases, n equals 1, answer is 0. Now we just have to handle 2 is less than or equal to n is less than or equal to 3. And the way we can do this is, we can essentially kind of do this with a bitmask dp. What this means is that we have dp of I and j, where we're at column I, or we've filled out the first I columns in a valid way, and the bits of the last column were j. So what this means is, let's say we have some sort of way to fill in the matrix, and then the previous column we had was 0, 1, 1. Now what we'll do is we'll convert this number to binary. So 0 times 2 to the 0, that's not a number, 2 to the 0, 1 times 2 to the 1, 1 times 2 to the 2. And this becomes 6. So what this means is our bitmask is going to be 6. So we also have that in this constraint, if we zero index, then we're going to have at most m columns, and j is going to be at most 2 to the n, which is 4 or 8, because there are only going to be 2 or 3 bits that we're concerned with. Yeah, there are only going to be 2 or 3 bits that we're concerned with. So that's what we do. Now we need to figure out a smooth way to implement this, and we can do it mostly with like some bitwise magic. Essentially, I'm gonna kind of go through my own code here because it's doing system testing, and I've passed A and B already. Sweet. Yeah. So one thing that's useful is you create a function that basically counts the number of bits you have to change to make A into B. For example, keep doing this. So for example, you have the bit mass 0, 1, 0 and 1, 1, 0. So to convert A to B, all you have to do is change this bit to 1. So what we can do here is we can use the property of XOR. If 2 bits are the same, then they're going to be a 0 in the XOR. So for example, 1 and 1, or actually I'll just do all the cases. 1 and 1 is going to be 0 because that's how XOR works. 0 and 1 is going to be 1 because they're different. Yeah, so 0 and 1 is 1 because they're different. 1 and 0 is 0. Both 0 because they're the same. And 1 and 0 is 1 because they're different. So now this XOR already can give us a way to count the number of bits that are different, because now all we need to do is count the number of 1 bits in this string. And there's a fancy STL function, there's a fancy standard function we can use called built-in pop count, which does exactly that. It just returns the number of set bits in a number. Yeah, so this gives us an easy way to compare the bitwise difference. I believe it's called Hamming distance. Yeah, so this is the Hamming distance between A and B. That vocab doesn't really matter, but this could be useful. Then, as you see here, we have the special cases. Then first what we do is we compute the bit mask of each column. And let's, for example, do that for the sample that we've doodled over. So this is the value of this row is 2 to the 0, 2 to the 1, this is 0, and 2 to the 2. So this is, which is 1, 2, and 4. So this is 1 plus 0 plus 4, which is 5. This is 0 plus 0 plus 4, which is 4. And this is 1 plus 2 plus 0, which is 3. So these are the bit masks of the rows. Then basically, we can have a formula for dpij, which is it's diff being the function that computes the difference between two numbers, the Hamming distance, equals diff j k. Actually, it's the minimum of all k. Okay, I kind of screwed this up. So this is the minimum over all k of diff j k plus dp I minus 1. Actually, it's the minimum of all k and x, where it's difference between j and k plus dp I minus 1 x. And we can only include this running out of colors here, kind of. If the columns that are created are valid, that is, the columns X and K in that order are valid. So this formula is relatively straightforward to compute. We already have a way to check. We have a way to compute difference, and because of the way dp works, we've already computed dp I minus 1x. For the first column, since we don't have this, it's just simply we ignore this and just it's the minimum. dpij is, or dp0j, I'll write this out in another different color. dp0j equals diff. We're going to use mask to represent this. Sorry for my mouse writing. Is diff of mask 0. Oh wait, actually, yeah, this should be not. Hang on, I think I messed that up. So dp0j is difference of mask 0 and j. And this is slightly messed up. What this should be is, since j is fixed, it's the minimum over all k of diff. Since we're already in this row, we already have the mask of mask I. And j plus dp I minus 1 and k. That's kind of flowing off the screen, but whatever. Now that's correct. And at the same time, the columns jk have to be valid. Or it would be, I guess, kj are valid. Okay, now all we have to do now is check if columns kj are valid, and that means that the submatrices have to be odd. So I'm gonna grab a bit more space down here and lose my mouse apparently. Now how do we check for validity? Let's say we have the masks 1, 0, 1 and 0, 0, 1. So we want this square to have an odd number of odd number of 1s, and this square to have an odd number of 1s. If n equals 2, then we only need, obviously we don't need to check the second square because it's not there. So what we can do is, we're looking for the number of 1s in these two bit masks, right? So, however, we're only looking for the number of 1s in these 4 bits specifically. Or even more specifically, the first and the second bit of this. So the first bit has value 1, and so the first bit has value 1, and the second bit has value 2. So what if we can use a bitwise AND operator to only capture these bits? And essentially we can use the value mask and, trying to draw an ampersand with my mouse, mask and 1 plus 2, and that will give us only these bits, only the bits with value 1 and 2, and not 4. So that's why in my code, that's why I take mask, and when I is 0, this will be 3. So this will take the value of mask and 3, which will extract only these bits from the two numbers we're interested in. And similarly, when we're trying to find, ignore the green separator, this one will take mask and 2 plus 4. And that will give us exactly these two pairs of bits. Or yeah, these two pairs of bits, which is what we're interested in for the second square. So in my code, this will be val equals 3 plus 1 plus 1, which is 2, which is 3 times 2, which is 6. So this will be the previous mask and the new mask j and 6. And we also use built-in pop count to just count the number of ones in these bit masks. Then we check if it's even, we say it's not possible and stop. Otherwise it's odd, so we continue it being possible. Then if it's possible, we just set exactly this. It's diff plus dpi minus 1 and k. Then the final answer is, over all ways to set up the last column, it's the minimum, use another different color, minimum ants equals minimum over all k of dp, the last column m minus 1, and k, which is what we're doing here. Then we just print the answer. That is slightly complicated, but that is how bitmask dp works. My code is going to be in the description so you can see exactly how I've implemented all of these. If you are still confused, you might want to check that out because it basically does all of the things I explained here with this magic, bitwise magic with built-in pop count and the XORs and the bitwise ANDs. Okay, I don't have a solution for E, unfortunately. I guess you can check out Second Thread's video for that since he probably explains it. Yeah, that's about it. That's about it for this contest. I enjoyed these problems generally. They were more interesting to think about, like A, for example, being a troll problem. They had some observations. Not really a big fan of combinatorics, but I mean, some people like it, so I can't complain too much. B was at least observational, so it's more than just implementation. In fact, it's a simple implementation. You just check the last row and the last column. And D was a good mix of implementation and some observations that you have to do. So overall, I liked it. Yeah. Wow, that's a lot of fails. So that does that. I guess I'll put my final rank in the description. It's gonna be better than last time, at least double digits, which is always a good thing. Let's see. So what will we do next? I think there's not really a point in me screencasting this because I don't want to do commentary since it's a rate of round. So I'm just going to upload solutions for this one. I can screencast the edu round. This one I tested technically, so I can't participate in this. And then if there are more rounds before this one, I'll do those as well, and I'll also do this one. So that's it in terms of screencasts. You can also expect, there should be a few like cool tutorials around. I think the first topic I'll do is heavy light decomposition. Look forward to that. Yeah, that is about it with this round. Hope you enjoy watching, and see you guys.